initial education, the graduation from the University Federico II, Naples, joined in Swiss Federal Institute of Technology in Lausanne, Switzerland, and he has earned his PhD from EPFL, Switzerland, and then 2002 onward he is in Imperial College, London, and he has made sampling, that is a new kind of you can say non-uniform sampling, and a new technology that how the signal can be represented and thought in a different way. So today's talk is also based on that new sparse sampling method. So now let us join to hear the Professor Pier, Luigi, Dragotti. So welcome, sir, to join in this session and deliver the talk which will benefit all the members of IEEE Society.
Thank you very much. Thanks a lot for the nice introduction. Let me try and see whether I managed to share my screen. Okay. Sorry.
So on the right hand side below, there is an option called present now.
Yes, I think the problem is that, okay, why this is not allowing me. Okay, so you're not seeing my screen, right?
No.
Okay, yes.
You select that, and
yeah, I think I had some. Okay, let me try this again. Nice. One second. Yeah, kind of.
As now more number of attendees are joined, so I again announce them. The attendees are kindly requested to turn off your camera and mic so that we can start the talk. And well, before the starting presentation, I would like to mention that the question answer session will be discussed after the talk. So attendees are requested to leave or drop their questions and queries in the chat section below. So we welcome you all.
Hello, sir. Yes, sir. Just now you also presented your screen.
Okay. Yes, I think I should be able to do that now. I apologize. I normally don't use Google, so that's why I had some issues there. But I think we should be fine now. Give me 1 second. Okay, can you see my screen?
Yes, sir.
Okay, let me see. Okay, so can you see the slide? Yes.
Yes, sir. The slides are visible.
Yes, sir.
Yeah, I think we are good to go now.
Yes. Okay, good. I guess. Okay. Thank you. I apologize for these little problems. So thanks again for the invitation and give this talk. And the idea is that I'm going to give you an overview of the work I've been doing over the last 10, 15 years in the area of sparse sampling. And I will first give you an overview of what I've done a little bit in the past, and then I'll focus on a couple of topics of current interest. One is about bio-inspired sampling, which we also call time-based sampling, and another is related to sampling at non-uniform locations, but in particular when the locations are along a trajectory which might be also unknown. As I mentioned, this is work that I've been doing over many years, and so I should acknowledge many of my students who worked on these topics, and also some collaborators, in particular Martin Betterly from EPFL in Switzerland, Thierry Blue from Chinese University of Hong Kong, and Simon Schulz, who is a neuroscientist at Imperial College. Okay, so what is the problem? Why something is interesting? Okay, so we know that we are seeing more and more sophisticated new sensing systems appearing, and they offer us the opportunity to have access to the physical world, maybe at unprecedented resolution. Yet these new devices also bring new challenges, which forces us to perform sampling and reconstructions in different ways. So let me make a few examples, a little bit linked also to the type of research that I've been doing over the years. So the first example is in the area of microscopy, and in particular two-photon microscopy, which is a specific type of fluorescence microscopy, which is used for example, monitoring the activity of neurons in the brain. And so let me give you an idea of the type of signals that we get. So this is the type of signal we see. It's like signal over time. And so here you can see that there are these regions that become brighter. Okay, these are like neurons. And then in neurons, when it is active, it generates a pulse, which is known as action potential. And so we need to work out when a neuron is firing, because by analyzing all these activities, we can try and understand how the brain processes information. Now, if you focus on a single neuron and then you look at the evolution of the signal over time, then you will get a signal that looks more or less like the one shown here. So it is a sort of a stream of pulses, which are really a stream of action potentials. Now, the problem with these technologies is that since the region here, the tissue, is illuminated through a raster scanning technique, then what happens is that we can get very good resolution in space, we have very good resolution in time. So we need to develop methods that are able to enhance the resolution in time and to retrieve when the neurons were active at very high resolution. So even though the technology has great potential, still has some limitation that requires us to act. Another type of microscopy, which is quite interesting, even though I won't cover it in this talk, is electron microscopy, which allow us to see things which are even smaller than neurons. And for example, it can be used to work out the shape of viruses, okay, for example, coronavirus, okay. Now, the way this microscopy works, in particular, one version of it, which is known as cryo-EM, cryo electron microscopy, is essentially that you get projections on a plane of, let's say, the shape of your 3D objects, and you get many such projections. The problem is that you do not know the direction of these projections. And so you're faced with the problem that not only you need to reconstruct the signal, but also work out the direction of the various projections. So this is really a problem in some sense of sampling when you do not know where you took the samples. Okay, and that's a common problem that happens in many applications. And I'll show you another application in a second. Definitely also of interest in general are sensor networks, which are used to monitor physical fields. typically, for example, the diffusion fields, which would model, for example, the distribution of the heat. And so you can have sensor to measure temperature at a few locations in a certain region, and then you'd like to see the distribution of the heat in the entire region. But can also be used to, for example, monitor the fallout or the dispersion of biochemical agents. And so ideally you'd like to have sensors that sense this biochemical agent and then can work out, for example, the location of where the dispersion is happening, but also, for example, the timing, so when the dispersion started. Now, especially in contexts like this one here, and in similar contexts, maybe what you're going to do is actually you're going to use an autonomous vehicle, maybe a drone, which is going to monitor the region by flying in the region. So here is an example where you have maybe a fire, okay? And then based on the measurements that the drone is taking, then you want to reconstruct the fields of interest. Because of that, obviously because of the nature of the acquisition, then here you are in the context where the measurements you take are extremely concentrated in some areas, but then you do not have measurements in other areas. So you have a form of sampling which is extremely non-uniform. And in particular here, you're really sampling along a trajectory. And so the fundamental question is whether you can reconstruct your field by using measurements that you've taken along a trajectory. But the other problem is that in some cases, you do not know the trajectory itself. You know that the drone was moving, but if you have no GPS, for example, you don't know where the drone was, and therefore you do not know the trajectory. So here we are back to a problem, you know, similar to the problem that I mentioned here, where you get some measurements and you want to use them to reconstruct a signal or a phenomenon, but you do not know where these measurements have been taken. Okay. And so I will cover some aspect of this problem toward the end of the talk. So let me sort of draw a few high-level observations out of these few examples. So the first important observation is that the real world, the physical world, is analog. But then we get samples, measurements, which are essentially digital, and then we do computation on these measurements. But key for us is really to understand the interplay between these two domains, because when you understand this interplay, then you can do computation in a more efficient way. And so you really need to understand how to go from one domain to the other. And sampling theory really provides the framework that connects these two worlds, and therefore give us the framework to then do computation in a more efficient way. The other thing that I would like to stress is that that's something that we tend to forget nowadays with the advent of machine learning, etc. So we tend to get the data and then just do some processing, forgetting about the origin of the data. But as these examples have shown, most of the data we play with are signals generated, so it could be biomedical data, you know, activity of neurons, heartbeat, etc. Could be video sequences, so multimedia data, physical measurements like temperature fields, etc. And really understanding the origin of the data is very often important if we want to do any form of data processing or inference, which is something that we tend to forget. And so that's why something is actually useful, because it forces us to keep this aspect in mind and to always try to remember where the data is coming from. But okay, having said all that, let me give you a sort of roadmap of the talk. First of all, I'm going to give you the standard setup for the sampling problem. And then based on that, I'm going to briefly review the traditional approaches which would lead to the Shannon sampling theorem. And then I'm going to talk about the more recent theory based on sparsity and what we call sparse sampling, and introduce a specific class also of signals which are known signals with finite rate of innovation. This will also be used as a building block to then look at some recent development in the area of sampling. One is about energy efficient sampling or bio-inspired sampling, and the other is about sampling along trajectories, where in both cases we're going to leverage results in sparse sampling theory to get new sampling reconstruction methods. Okay, so let me see, can I remove this? Sorry. Okay, I think this is better. Okay, sorry about that. Okay, so the typical sampling setup is shown here. So the idea here is that you observe a certain signal, and the signal is obviously continuous. And then you observe it with a certain acquisition device, which we assume is a linear behavior. Now, this may model, for example, the distortion introduced by a lens in a camera. So it's a linear system with a certain unit impulse response. So this introduces some form of distortion, giving you a new signal y, which you then sample, and this leads to the samples yn. So the fundamental question in sampling is under which condition I can claim that there is a one-to-one mapping between the samples yn and the original signal xt. And what classes of signals xt would allow me to have a one-to-one mapping, what type of acquisition devices I need to use, and finally, if there is a one-to-one mapping, what type of algorithm should I use to reconstruct the signal x from the samples. Let me also highlight that if we use this framework here for the, let's say, sample formation process, then the samples can be seen as inner products between the signal x and the time reverse version of the unit impulse response here, which we call phi and we call sampling kernel. So the samples are the inner product between x and phi, but also uniform shift of phi, where the shift is related to the sampling period. We can see these results were just expanding, let's say, the equations related to this model. So y is obviously the convolution between x and h, because this is a linear system. And then given y, we take samples at a uniform instant. So this gives us the samples. And now if I replace h with phi, which is essentially its time reverse version, I am turning essentially a convolution into an inner product. And so I end up with this result that yn can be seen as linear product between x and shifted version of phi, but the shifts are uniform. And phi is something that we call the sampling kernel. Okay, so given this framework, the question is, can we reconstruct some signals? And the original answer, which led to the more traditional sampling theorem that we sometimes call the Shannon sampling theorem, provides a positive answer under the assumption that the real-life signals x should always be modeled in this way. So should always be seen as a linear combination of a single prototype function and its uniform shift. Now, signals that can be modeled in this way, we say are signals that belong to shift invariant subspaces. But specifically, if phi is the sinc function, then x is a bandlimited function. Okay, so the bandlimited functions we're used to can all be modeled using this model here. And then, if we accept this model, then we end up with the standard, let's say, Shannon, let's say, sampling and reconstruction process. So you would have your x, then you have a first filtering. That models really the acquisition process I mentioned before, but in the context of Shannon sampling theorem, you can think of this filter as an anti-aliasing filter, and then you sample. Now, given the samples, you can achieve reconstruction through a simple linear process. And that's because x belongs to some linear subspace. And therefore, you can reconstruct linearly, and the shape of this filter depends on this prototype function phi here. So in the bandlimited case, phi would be the sinc function. So here, this is the sinc function. That means that this filter is an ideal low-pass filter. Now, the problem with the traditional approach is that the classes of signals we can play with is a little bit too limited, okay? The major issue is really this idea that I have a prototype function and then I have to look at uniform shifts. So that would mean, for example, that if we were trying to model images in this way, then we can only consider images where edges are on a grid, okay? So only at uniform different locations. Whereas we know that edges in images can happen everywhere. So the fundamental limitation here is that here we are forced to have uniform shifts, whereas we would like to have some non-uniform type of shifts. So that's why people try to come up with slightly more general models than the one used in the traditional way of doing sampling. And in particular, there was then this idea of sparsity that appeared. And so the idea is that maybe we could have signals which are not bandlimited, but that we can be sparsely described. What we mean with that, for example, these are signals that are completely determined by a small number of free parameters. Okay, so since it's a small number, these signals are sparse. Now, one classes of signals that fall within this model is shown here, okay? And if you look at this expression here, it's very similar to the one that we had before. So there's a fixed prototype function phi, which we know a priori, and then I have linear combination of shifted version of this phi. The major difference is that now the shift here can happen anywhere, okay? And so if we were to introduce a two-dimensional version of this model, that would lead on to images that can have edges at any arbitrary location. So it's actually a much more general class. But also, for example, this type of model can represent, for example, stream of pulses, where phi would be the shape of the pulse, and then the pulse can be located anywhere, and the amplitude of the pulse can be any amplitude. But this signal can also model, for example, piecewise polynomial signal. So, for example, a piecewise constant signal where edges can be at arbitrary locations. So you can have, for example, two arbitrary close edges. Now, the idea is that we call this type of signals with finite rate of innovation, and the reason is because if, for example, we think of the case of a stream of pulses, if there is a finite number of pulses, let's say there are only k pulses in the signal, then I only need 2 times k parameters to reconstruct this signal exactly, because I only need to find the k location of the pulses and the k amplitudes. So that's why this signal has only a finite number of independent, let's say, parameters that we need to retrieve, and we call it signal with finite rate of innovation. And so since we have only a small number of parameters, then the intuition is that if I sample these signals and I have enough samples, then I should be able to retrieve these free parameters from the samples and therefore reconstruct the signal. The key question is, how am I going to do that? How am I going to achieve the reconstruction of these parameters from the samples? So the core approach in sparse sampling is to try and map this problem of retrieving these free parameters to a method which is broadly used in engineering, especially in array signal processing, which is known as Pronis method. Okay, so in Pronis method, what happens is that you have a set of measurements as m with this type of shape here. So it's a finite sum of exponentials, okay, uk, to the power m, where m is a whole number, okay, is an integer. Now, Pronis method allows us to retrieve the bk's and the uk's from this sequence here. So let's assume that our signal that we are interested in is a stream of pulses, okay, idealized pulses, so they are Diracs. So we're after the location of the pulse, tk, and the amplitude of the pulse is xk. So what we want to do is, given the samples, we would like to map the samples to a new set of measurements Sm with this type of shape here, where the uk here encapsulates the information about the location of the pulse, whereas the bk encapsulates the information about the amplitude of the pulse. Because if we can do this mapping here, then we feed this sequence to Pronis method, and then the Pronis method will produce the bk and the uk's, and then from the uk's we retrieve the location of the pulses, and from the bk's we retrieve the amplitude of the pulses, and then we are solved the problem. Create to do this mapping, and we can achieve that by taking our sampling kernel phi, and then we try to find coefficients cmn such that if I take a linear combination of uniform shifts of phi with these coefficients, then this sum leads to a complex exponential. So let me try and show you sort of visually what we're trying to do. So let's assume that the shape of phi is a shape like this one shown here. Okay, so that's our sampling kernel. Then what we do is we take the sampling kernel like shown here. We take uniform shift, so this is a shift, this is another shift, this is another shift. And then we take a weighted sum of these uniform shifts. So the weighted sum leads to a new function, which is the one sketched here. And what we want is that this function is a complex exponential. So it's something that oscillates like what is shown here. And then the idea is that if I change these coefficients, I reproduce a new exponential with a different exponent. So for example, I have again a function that oscillates, but maybe more quickly. Okay. So can I achieve that? How can I find these coefficients? So the point is that we're trying to find coefficients such that this sum is sufficiently close to a certain function, which in our case are exponentials. So if you want to minimize the error in our approximation in the least squared sense, then we can do this by computing an orthogonal projection. So we need to project the function that we're trying to approximate onto the subspace which is covered by the sampling kernel and its uniform shift. So once we realize that we're trying to compute an orthogonal projection, we can use the orthogonality principle of the orthogonal projection theorem that really says that the error in our approximation, which is shown here, should be orthogonal to this subspace. So it should be orthogonal to phi and its uniform shift. So in the end, we need to find the coefficient Cmn that would satisfy this set of equation here. And so given this set of equation, we can then find these coefficients. And what is interesting is that in this specific context, because we have uniform shift here, and because f is a complex exponential, then one can end up with a closed form expression for these coefficients. So a closed form expression for the coefficients that are going to give us the best possible approximation to this problem, okay, which we derived a few years ago. Okay, so we now have the coefficients, okay. Remember that these coefficients depend on the sampling kernel, not on the signal. Therefore, that's something that we can derive at the beginning before doing any sampling. But now, once we have these coefficients, then what we do is we just take the samples yn, and then we compute linear combination of these samples using the coefficient that we found. So that will give us this new set of measurements. Now remember that the samples are inner products, okay, between x and the sampling kernel. And using the linearity of the inner product, we can move this sum here inside the inner product. So these new measurements are really equivalent to this inner product between the original signal and this quantity here. But this quantity here, because of our choice of this coefficient, is approximately equal to this complex exponential. So really what we have is that we have these new measurements which are obtained through this sum here, but this sum here is really equivalent to computing this integral. And now if I replace x with its expression here, it's a stream of pulses, then I discover that this integral is exactly equal to the sum of exponentials that we can use for in Pronis method. So let me summarize quickly about the core approach. Remember, we observe our samples yn, and then what we do is, since we know the sampling kernel, we compute these weighted sums, okay? So we have our coefficient Cmn, and then we compute these different weighted sums, and they lead to this new quantity, Sm, and then Sm, we realize that by construction, have a shape which is equal to this sum of exponentials, which we can then be fed into Pronis method, and then Pronis will give us automatically the bk and the uk's, and then from the uk's we retrieve the locations of the pulses, and from the bk's we retrieve the amplitude of the pulses, and so we solve the problem. Now this is the canonical case, it's the simpler case, okay, a stream of Diracs, so it's a very specific type of pulse, okay, but actually this framework here can be extended to many other signals and can be used also in application. So let me show you some examples, okay? So in all cases, the approach is always the same. There are only some minor variations. So let me start with an idealized setting. So here we have an idealized signal. These are pulses, okay? They are pulses with very fast phase and very slow decay, okay? And we have 4 pulses here. Now, remember, this signal is filtered with our sampling kernel, and then we take samples of the filtered signal. So the samples are these black dots here, okay? So the approach is that you then, given these samples, take weighted sum, okay, of these samples, and this will give us a new set of values which are in the form which is useful, which can be used with the Pronis method. So then these new measurements are fed into Pronis method, and Pronis method produces essentially the location and the amplitude of the pulses, and therefore, given the location and the amplitude, we can reconstruct the signal with no error, okay? Now that's again an idealized setting, okay, but let's look now at some concrete cases. So let's go back to the problem in neuroscience I had mentioned before. So here we have our signal in time. This is a stream of action potentials, and action potential are pulses, so this is really a stream of pulses. However, these are very low resolution, okay? The sampling rate here is 7 Hz, so it's very low. And so we'd like to retrieve the location of these pulses at very high resolution. Now the good thing is that in this case, okay, we also have access to the ground truth location of the action potentials, because there is a specific way in which we can acquire the data that allows us to know at high resolution the ground truth location of the action potential, so that we can compare our results with the ground truth. Okay, and so here in red I'm showing the location of the pulses that we detected, and in blue I'm showing you the location at high resolution of the original action potentials. So you can see that sometimes we miss an action potential. So here there are actually two pulses and we find only one, but besides that we can find them so our detection success rate is good, but also at very high resolution. And in fact, if we compare, and how do we achieve this? We achieve that by using the idea that I mentioned before. So you take all these samples, you take these sort of weighted sums, and then you sort of send this to Pronis method, and Pronis method produces the locations and amplitude of the racks. Obviously here we are operating on real signals. They're very noisy, so this basic method needs to be modified a little bit in order to increase resiliency to noise and robustness of the method, but the core idea is exactly the one that I mentioned before. If we compare this with other methods, we realize that this new approach is better at detecting pulses than existing method, is actually also very fast, but also that the location that we find, okay, is at a resolution which is on average 3 times higher than the resolution given by the device. So essentially, through something we can essentially provide data which are those that you would obtain if you could scan your region of interest at a speed which is 3 times higher than what the actual microscope is able to do. So that's one example. That's another example now on images and again on real data. So this is an image that we took with a camera, a good quality camera, an image that we took ourselves. So that's a picture actually of the Victoria and Albert Museum. So it's a museum in London. And here we are just looking at the specific region of that image. So some decorations of the palace. And then obviously, even though the camera is a good camera, when you look at the very small feature, then if you try to look at it more in details, then you can see that let me show you another example that's related to, again, sensor network in this case. So we have sensor here measuring a temperature field over time, okay? And so if we concentrate on 2 sensors, this is the type of data that we see over time. Now, the field here, this is real data, but is obtained in a very controlled environment. So what we did, we had a silicon plate, and then we use a heat gun to create a heat source, which is very concentrated in space and time. So when we have the heat source, then the temperature in the sensor is growing, as shown here, especially if the sensor is close enough to the source. Okay, and the question is, given these measurements, can we reconstruct the entire field? So let me show first of all the evolution over time of the measurements. So if you look at these few pixels, at a certain point you can see now that they are becoming brighter. Okay, so this is when the event is happening. Okay, and so now the question is, given this information, can we retrieve the entire field? Now the good thing is that we have the ground truth data here, because we obtained the data by using a thermal camera, which can see how the temperature evolves over time. And then our sensor here, which we use for our reconstruction, are only a few pixels, right, in the complete video sequence. Now, from these few pixels, okay, by looking at the evolution over time, we are able to reconstruct the signal, which is shown on this side. This is the ground truth data, okay, and as you can see, the reconstruction is extremely accurate. Now, that can sound maybe surprising, but you need to realize that this problem is extremely sparse, and this is really what helps us a lot. Because essentially, remember here, we are after only one source, which is concentrated in space and time. So we are really just trying to retrieve a very small number of parameters out of all our sensor measurements. And so even though the problem can look extremely ill-conditioned, because we have this very strong prior, then we can be very efficient. So that's so nice. I think that gives you some evidence of the impact that we can have in practice when we develop new sampling results. Okay, so you can have impact in neuroscience, or in imaging, or maybe in problem related to the use of sensor networks. However, as I mentioned at the beginning of this talk, there are still new and new challenges that emerge with the progress in the new sensing devices. And I would say there are a couple of important challenges that I want to cover in the rest of the talk. The first one is an issue that in the way we currently do sampling, we are very energy inefficient. So why is that? Because, for example, each time we want to monitor a fast event, okay, so for example, take a video of a bullet like it is shown here, then we need to have, for example, a camera that operates at very high frame rate, okay, so takes an image very quickly. And so when you increase the frame rate, obviously you end up producing a huge amount of data, and so that consumes a lot of energy. So we have this issue that if we try to improve on the latency, so if you want to be very fast, introduce low latency, then we end up being very energy inefficient, consume a lot of energy. So we need to find a way to break this problem and try to be able to sample quickly, but also in an energy efficient way. And the other problem, which I mentioned at the beginning, is a context where sometimes when we sample at unknown locations, but also that sometimes the samples are taken in some very concentrated regions, but we have no samples in other regions. And so the problem that I'm going to look at is the problem where I try to reconstruct a diffusion field, so for example a temperature field, from measurements taking along a trajectory, and the trajectory is also unknown. Okay, so let's focus first of all on this issue of energy efficiency, and let me try and show you why current approaches are inefficient through a simple example. Okay, so let's assume that we want to estimate rainfall, okay, over a certain period of time. Okay, and let's assume that we want to measure rainfall in a country like Greece over the summer, and we know that in Greece over the summer normally doesn't rain very much. Okay. Okay, so now the way we would do that is, for example, is by putting a bucket in our maybe back garden here, and then measure how much of rainfall drops in the bucket at regular time intervals. So for example, every 10 days. So on July the 10th, for example, we measure how much rain is in there, we empty the bucket, okay, and then we repeat the process. So we have the emptied bucket, and then we wait, let's say 10 days, and then on the 20th of July, we check how much rain is in the bucket, we store that information, we empty the bucket, and then we repeat the process. Okay? Now, what is the problem with this approach? The problem is that if I am, for example, in Greece over the summer, then very likely at a certain point, there will be no rain for a long period of time. And yet, even though there is no rain, I still need to take measurements at regular time. So I take a measurements here, and say, oh, the bucket was empty, another measurements here, just to say that the bucket was empty, and then maybe I have some rain at the end of the month. Okay? So I'm becoming inefficient because I keep taking measurements, even though there has been no event of interest, there has been no rain. And obviously things become even more problematic when I try to maybe sample more precisely. So for example, rather than taking a measurement every 10 days, maybe I try to take a measurement every day. And if I do that, maybe during the month of August, I'm going to take 20 or 30 measurements, all about zero, right? Because there has been no rain whatsoever. And so that's why this method is very inefficient. So what is an alternative to that? So the alternative is the following. The idea is that I still put my bucket, but then rather than checking it at regular time, I leave my bucket in my back garden, let's say, and then I wait for the bucket to be full. When the bucket is full, then I write down the time when this happened, let's say on the 18th of July, and then I empty the bucket and I repeat the process. Okay? So process, so I don't do anything until the bucket is again full, which maybe happens on the 28th of July. So on that day, I write down the time when this happened, and then I empty my bucket. Now the interesting thing is that if at a certain point there is no rain, which is really in this case because we saw that in August there was essentially no rain, then what's going to happen is that I don't have to do anything throughout the month of August because the bucket won't become full because there is no rain. And then I'll have to wait maybe sometimes in September when eventually the bucket will be full again. And then again, what I do, I write the date, so the timing information when this happened, and then I empty my bucket and I keep going. Okay. So this approach is clearly way more efficient because what happens is that I may get way more measurements when, for example, there is a lot of rain. So when there is an event happening. But then if nothing is happening, I don't take any measurements, and so I save a lot of energy. Now, this is the way nature operates, and in some sense, this way of operating is also known as integrate and fire. Why is that? Because essentially, when I fill the bucket and I wait for it to be full, I am sort of integrating the information, and then when the bucket is full, I fire, to use this idea. So I write down the timing, and I reset the system. So I empty the bucket. Okay. Now, this is the way, as I said, first of all, integrated file system works, but it's also the way in which, for example, neuron represents sensory information, because we know that the neuron integrates some information, and then when you reach a certain threshold, it fires, it generates an action potential. And so the information is stored in the timing of these spikes on when I fire. Okay, and also, as you can see here, I fire in a very asynchronous way, non-uniform way, and so when there is an important event, I fire a lot, and then nothing happens when there is no event. And we know that the brain is extremely energy efficient, so we would really like to try and mimic this way of representing sensory information. So for us, we need to address these fundamental questions on whether it is possible to embed information related to complex signals into this timing information, so the timing of when I have these spikes. But let me also stress that now people are also trying to actually create sensing systems that mimic the way the brain works. These are very often known as neuromorphic sensing devices, and a specific type of device is a video camera that is based on this idea. These are known as event-based cameras. And what happens in these cameras is that you have that the pixels behaves like integrate and fire. So essentially, pixel does not do anything, does not fire if you are taking a video, for example, of a static scene. But when there is some movement, and so there is a change in the luminance, then the pixel will fire. Okay? And since you can have a good resolution of the timing of the firing, you can end up with a video sequence which is virtually at a very high resolution and will allow you to measure fast events consuming not much energy. So here is an example of a video obtained with these cameras where you can see here in slow motion a coin flipping. Okay, so this camera takes this video of this coin and can give you, can describe nicely this fast event. So for us, the question is, given this type of sensed information, is it possible to reconstruct the original signal? So can we reconstruct the original intensity video, which is not there, at this resolution? Okay. So even though we're not able to address the video question yet, we can address the question for some specific 1D signals. And let me try and give you an idea. Okay. So first of all, this is the model of the system. Okay. So that's a standard model. So you have your signal coming in, we assume it's a 1D signal. You integrate, and then when the output of the integrator reaches a certain threshold, then you fire. Okay? So you have a certain threshold, which is known as trigger mark. Then when you reach that threshold, you fire. So you generate, if you want, a spike, and then you store the time of that spike. Okay? So you have a spike here, then you can have a negative threshold, so the spike here, and so on and so forth. Since you know the threshold, you know in some sense the amplitude of this spike, and then you hope to be able to reconstruct the signal X from this timing information. Each time you fire, then you reset your integrator. So that's the basic way in which the system works. There is another system that does something similar, which is known as the comparator. From a practical point of view, the comparator is a little bit less interesting, but from a mathematical point of view, it's a little bit easier to analyze. And so sometimes it's better to look at the comparator and then extend the results to the integrate and fire case, okay? Because the framework is actually essentially the same. So in the comparator, what you do is you have your signal, and then you compare it with a reference signal that you know. So typically, this is a sine wave at the frequency that you choose, okay? So you take this difference here, and then you store the time when this difference is equal to 0, okay? So here that's shown visually, so that's your signal X. This is the comparator signal, and so at this location here, and then at this location here, here, and so on and so forth, the difference of these two signals is 0, or if you want, these two signals are equal, okay? Now, because of that, from this timing information, you can retrieve back some information about the amplitude of X, okay? Because obviously, you know that you are firing when X was equal to G, and you know G, okay? So at each time, this time instance, you retrieve the amplitude information about X, and then the question is, can I reconstruct X from this amplitude information? Obviously, as you can see from here visually, the timing here are non-uniform. So you really end up with a set of samples which are non-uniform. And the question is, can you reconstruct X from these non-uniform results? Now, historically, this problem was already addressed, again, in the case of signals belonging to shift invariant spaces, okay? So that's the non-uniform equivalent of the sampling theorem, if you want. And so this problem was addressed by Aldruby and Dragotti. And again, here, the idea is that your signal X can be modeled in this way. And so remember that if phi is, for example, the sinc function, that means that X is the band-limited function, okay? And so they provided condition on how many samples you need to have here in order to get perfect reconstruction. I want to give you an idea on how this is achieved. And so let me go back to this example here to give you an idea of how reconstruction is achieved, okay? So remember that we have stored this time information here. And so, for example, after July the 18th, we have emptied the bucket, okay? So in this instant, the bucket is empty, and then we know that it was full again completely on the 28th. So we know what is the total amount of rain that dropped over these 10 days. So one thing you can do is to say, okay, let's assume that it was raining constantly over these 10 days, and then you can work out how much it was raining, because you want that the integral of this rain is exactly equal in some sense to the volume of your bucket. So that allows you to get a first estimate of the rain that you see in these 10 days. Then you can use the same type of idea to work out how much rain dropped in this interval here, because remember that from here to here, okay, it rained enough to fill the bucket. And so again, you assume that maybe it was raining constantly, okay, uniformly, and so that's the signal that you reconstruct. So with this approach, you end up with a very rough, piecewise constant reconstruction of the rainfall over a period of time. Then what you can do is to say, okay, I have a prior, and I know that, let's say, the rainfall is a signal that is band-limited, okay? Let's assume that it's a smooth signal and is band-limited. So what you can do, you can say, okay, since this guy is not band-limited, I project it onto the spaces of all band-limited function. And that will give me a new version of my signal, something which is smooth, like this guy here. Once you've done this, you check whether your new signal would lead to the bucket being full at the time that we have measured. So essentially, whether this new signal is consistent with your measurements. If it is not consistent, you then correct for the error, and then you repeat the process. So let me show that visually. So here is a signal which belongs to a specific subspace, okay? And then through integrate and fire, we essentially sample it non-uniformly. So what we do this piecewise constant approximation, as I showed you before, and then we project this onto the correct subspace, and so that will give us the red line. Now, given the red line, we re-estimate the samples that we would measure, and then check the error, okay? So there is an inconsistency here. Given the error, we do a piecewise constant approximation of the error, and then we project it into the correct subspace. And then we combine our first estimate with this error correction here, and that will give us this new signal. and then we repeat the process, okay? And then if I have a sufficient number of samples, we can guarantee that this process will converge, and so that eventually you reconstruct the signal exactly. Okay, so this is all very powerful. There are two fundamental issues, however, with this approach. First of all, in order to guarantee convergence, you need to have enough samples. And what it happens is that you need a density of samples here, which is higher than what you would need if you were doing uniform sampling, okay? So essentially, here you are, in terms of energy, even less efficient than uniform sampling. So we are completely defeating what we were trying to achieve, which was energy efficient sampling. The second issue is that, okay, we can sample band-limited functions, but as we've seen before, we would like really to sample more interesting signals like sparse signals, okay? So there are these two issues that we want to address, okay? And so the idea here is to leverage what we learned in sparse sampling to try and address these two issues, okay? So first of all, we would like to filter our signal before applying the integrated file system, and then filter it with a device for which we can then have a sampling kernel that is able to reproduce exponentials. And then we'd like to use, for example, Pronis method to reconstruct the signal. So this leads to this new framework here, where the incoming signals are signals, as we said, sparse signals, okay, with finite rate of innovation, so stream of pulses, or let's say piecewise constant signal. And now, before using my integrated file system, I filtered my signal, okay, with the filter with sampling kernel phi, okay. So now the idea here is that I want to set the system and the threshold in a way that when I have an event, so for example I have a pulse, then this event triggers a lot of spikes here. And I want to have enough spikes so that I can then reconstruct this event. But after that, I don't want the system to do anything, okay? So I don't want to trigger any further events until any further spikes, until I get a new pulse, okay? And similarly, if I have, for example, a piecewise constant signal, each time I have a jump, which is an event, then I want to trigger a lot of spikes here and reconstruct that edge. But then when there are no edges here, I don't want to trigger anything, because what I want to be is very energy efficient. So what I'm really trying to achieve, I want to have here spikes which are extremely non-uniform. So a lot of spikes when there is an event, and then nothing after that, okay? So if I focus on the integrated file system and I forget about the comparator, then really I can achieve this by making sure that I pick the right sampling kernel here, and to get the right density of instance, I need to pick the correct trigger mark. So the trigger mark must be low enough so that when I have some events, I trigger a lot of spikes, and then I have no spikes for a while, and then I have many spikes again, and so on. Right, so now I need a certain density of spikes. First of all, because of the type of model here, okay, one can show that given the timing information here, I can relate them to the inner product between x and phi as before, but now the shifted version of phi is a non-uniform shift where the shift is related to this time here, okay? So I would like, as before, to be able to reproduce exponential with phi. So I would like to satisfy this condition here, equal to the exponential. But now the difficulty is that the shifts here are non-uniform, okay? These are related to when the spikes are happening. Now one can show that it is still possible to reproduce exponentials, but the fundamental difference with before is that we need a good number of spikes in a short interval, and then in that small interval we can reproduce the exponential. But when we go outside that interval, we cannot do that. So we really need to be able to generate a good number of spikes in a small interval, which must be sufficiently close to when the events happen. So for example, let's assume, for the sake of simplicity, that my event is made again of pulses which are Diracs, okay? So what we need to do is to make sure that the threshold here is sufficiently low, so that when I have a Dirac here, okay, I generate immediately after the Dirac a sufficient number of spikes, so that I can reconstruct that Dirac from these spikes. Now, in the case of an integrated file system, I need to make sure that I have 3 spikes which are generated by this Dirac. The first spike is sort of used to reset the system completely in case there was still something in memory of what happened before of a previous event. And then the following two spikes allows me to reconstruct the derive, because remember, I need to retrieve two parameters here, the location and the amplitude of the derive. So if I impose some conditions on the signal here, so that, for example, the amplitude of the pulse is never below a certain minimum value here, by leveraging the properties of phi, I can find a trigger mark here that can guarantee me that I can always have at least 3 spikes immediately after the derive. Let me just try and show that to you visually. So here is our signal, so it's a stream of 3 derives here. The blue line is the filtered signal, which is then integrated and then fires. And then you can see that this first derive generates a sufficient number of spikes before the following derive. In this case, about 5 pulses as shown here. Then nothing happens until I get the following derive. And then given the following derive, the system generates the minimum number that I need, which is 3 pulses here. And then nothing happens for a long time. And then I have the last derive, which generates the right number of pulses. So given this group of pulses, I retrieve the first derive. This second group, I retrieve the second derive. The third group, I retrieve the third derive, and then I can reconstruct the signal exactly. I just want to show you briefly that this can be also used, for example, for a piecewise constant signal, as shown here. Now the kernel here behaves like an analog derivator, so compute the derivative of this guy, so that when this signal is constant, the derivative is 0, and so the integrator doesn't integrate anything. And so when the signal is constant, I don't have any fire. Okay. And so here is just the visual result. So this is the incoming signal. When I have an event, which is an edge, this triggers a sufficient number of spikes. Then nothing happens for a while until I have another edge, this guy here, and that triggers this other set of events, and then so on and so forth. And then based on these events, I can then reconstruct the signal exactly. Now, if the events are sufficiently spread, then the number of spikes I generate is extremely low. And so I end up with a system which is way more energy efficient than all the system based on sparse sampling theory or on classical sampling theory. Okay, I'm going to spend 5 minutes talking about this other problem, and then I think we can wrap up. Okay? So again here, remember, we are trying to monitor a certain region where maybe there is some dispersion of some biochemical agent, or maybe there is a fire. Okay? And the assumption is that we are monitoring it using an unmanned vehicle, so for example a drone, which is moving along a trajectory which we assume is piecewise linear as shown here, and we want to reconstruct the field and reconstruct this trajectory. Okay. Now this problem is actually similar to a problem which has been studied a lot in robotics, which is known as the SLAM problem. Okay, and SLAM stands for simultaneous location and mapping. So there was a problem studied in robotics where you assume you have a robot moving in a certain area and maybe taking images. And then at a certain point, the robot goes back to the starting point, and when it realizes that it's back to where it started, it's able to work out the trajectory that it has done and work out the mapping of the region considered. Okay. So here we have a similar type of setting, but rather than looking at images, we are looking at physical fields, and in particular like temperature fields, which are modeled through a specific equation, which is the diffusion equation. So first of all, let's look at how the field looks like. Okay, when we assume that it is generated by a single localized source. So imagine you have a single localized source here, which is a heat source, okay, and generate your fields a little bit like I showed you before. Then you can show that the entire field is regulated by the so-called heat equation, and so you have essentially this type of behavior. So the field looks like a Gaussian pulse, okay, and the spread of the pulse, so the variance of the pulse, increases over time. So if you look at the field over time, as shown here, you have a pulse centered at where the source was, and then this pulse becomes broader and broader and broader, as shown here, over time, and obviously the amplitude decreases. Okay, so now here we have our field, which is generated maybe by a few localized sources, and then we're measuring it by moving along this piecewise linear trajectory. Now, because of the properties of this field, if I look at the measurement that I would get along one trajectory, okay, oh, sorry, one piece of this trajectory, so one line. So these are the measurements that I would see, okay? So this is really a projection of my 2D Gaussian along this line here. Now this signal is a stream of pulses, okay? And we know how to reconstruct the pulses and how to retrieve the location of these pulses using the sparse sampling theory, which I introduced at the very beginning, okay? And so the idea is that once I retrieve the center of the pulses and I do this on all this trajectory, okay, then I can try and use this information to retrieve the locations of the sources and the trajectory itself. Now, the first observation is that this problem may look complex, but it's actually very sparse, and that's the good news for us. It is sparse because we have a finite number of sources to estimate, maybe 2 sources here. So we are after the location of 2 sources and the intensity of 2 sources. Okay. Moreover, the trajectory is piecewise linear, so I'm only trying to find the location of the vertices of this trajectory. Okay. So the problem is sparse. The second thing is, as I mentioned before, the projection of the field along one line leads to a signal, which is one of these sparse signals that we can reconstruct exactly using the standard sparse sampling theory. Okay. And so I can estimate the location of these pulses using the original sparse sampling theory I mentioned before. So the first thing we can do is, for each trajectory, the first thing we do is that for each of these trajectory, we estimate the location of the pulses. Okay. So this gives us these measurements. Okay. If this is the trajectory related to the, let me call it the first line, then I call this guy Y11 because it's due to the first source along the first line, and I call this guy Y21 because it's related to the second source along the first trajectory. And then I can do the same along all the other trajectories. Okay, so here is again the example. These are the 2 sources. Then I can retrieve Y11 and Y21, and then I can also obviously retrieve Y12, Y22, and so on and so forth. Okay, and now given all these Y's, I want to retrieve the location of the sources and their amplitude and retrieve the trajectory itself. So let me again give you a very high level idea of how this is achieved. First of all, we are assuming we are on the plane, as you can see, so we are in R2. Now let's denote with C the slope of one of these trajectory. So C is really like this vector here with unit norm. Okay, and clearly this vector is the difference between bj plus 1 and bj divided by the length of this line. Okay. Now the ykj that we have retrieved, remember ykj means the projection of the k source on the j line is given by this expression here. Why is that? Because bj minus sk is this vector here, and so when I take the inner product between this vector here and this second vector here, since this second vector has norm 1, this inner product corresponds exactly to this length here, which is ykj. So once I realize these geometrical properties, okay, then I realize that I can also look at these new values, which are differences between 2 different y's. Okay, so these are ykj, so the projection of the k source along the j line minus the projection of the q source along the same line j. And clearly this difference is given by this expression. So I create a matrix here where I have all the possible combination of the y's. Okay, so this is one entry of this matrix, and so this is the complete matrix. And then geometrically we can see that this matrix can be written as the product of these 2 matrices. One here has size 2 times L, and L is the number of lines, and this encapsulates the information about the slope, or if you want, the direction of each line. Whereas the other term here encapsulates the information about the location of the sources, and this has dimension k minus 1, where k is the number of sources, times 2, and again we have times 2 because the problem is on the plane, so it's 2-dimensional. So omega is a matrix of rank 2, and I can factorize it using the SVD. So given omega, I use the SVD and I factorize it, so I end up with this matrix here and this matrix here, so the matrix S and the matrix C. Given the matrix C, I can retrieve essentially the directions of this trajectory here, and there are two sources here. This is the data that we measure, so these are the two pulses along the first trajectory, these are the two projections of the pulses along the second trajectory, and this is the third trajectory. And in this example, we also have some noise. So this is the measurements we have access to. Through these measurements, we compute these projections, y, k, j, and then we use matrix factorization to retrieve the trajectory and the sources, and the reconstruction is relatively accurate despite the fact that we have some noise. And here is an example on real data. This is again the temperature fields that I mentioned at the beginning, and that we obtain. This is real data, and this is the type of data we measure along this trajectory. Okay, so there are 3 lines, and there is only one source, so each line gives us one pulse. And then given this, we retrieve the trajectory, which is the blue line. This is what we retrieve, and the red line is the correct trajectory. And then we retrieve the location. The true location is the x, and the estimated one is pretty close. Okay, I think it is time to wrap up. So my first point I want to make is that, as you can see here, sampling is in a very great shape. It's very alive and well. There are a lot of interesting problems related to current technologies that requires new sampling methods and new sampling theories. As you probably have noticed in all the results that I showed you, sparsity is really central to the way we do sampling. So given a problem, we need to model it and see whether we can sort of characterize the signal we are trying to retrieve through only a small number of free parameters. And then if that's the case, then we can then devise methods to sample that signal and to retrieve these free parameters. Now, when we look at real-life problems, we can see that even though we get devices which increase their ability to resolve small details, we always need more resolution. Neuroscience is a good example. We have great resolution in space, but then we pay the price in time. So we always need to come up with good sampling results that can give you high-quality reconstructions even at low sampling rates. We have many cases where we nowadays sample at unknown locations, and that raises new challenges, and this is very interesting. I mentioned the SLAM case is an interesting problem, and then I mentioned the case of electron microscopy, which is also very interesting applications. Sampling can be irregular, and the trajectory is the most extreme case where the sampling is extremely irregular, and that poses new challenges. Energy efficient sampling is still very much unexplored, and I think there is a lot of work that can be done there, and it is really essential for performing fast sampling. And with that, I think I can conclude. Thank you very much for your time and for your attention.
Thank you.
Okay. I'll stop sharing.
Hello? Am I audible?
Hello? I can hear you. You're a little bit... yes. I can hear you.
Thank you, sir. Thank you, Professor Dragotti, for his valuable efforts and time and in directing us towards a new sparse sampling method where we also being introduced the time-based sampling and sampling along with the trajectories, where we can also introduce to the core approach of sparse sampling. So we hope it will be useful in the research or work of the attendees. Even I am sure all the students will be benefited from this talk. So I also again requesting all the attendees, if you have any doubt or question, you can drop in this chat box.
Good evening, sir. So I have a question. So in case complex trajectories, like which is very much non-geometric in real scenarios. So in those cases, whether sparse sampling is really effective?
Yes, a very good question. So if I understand the question, what you are saying is that the trajectory I've considered is a very simple trajectory, situation, we use very complex trajectories, okay? And so, whether we can still do what we are doing, okay? So, I have a partial answer to that, okay? So, the problem is all the parametric trajectory, okay? Which is normally the case. So, it might be not necessarily piecewise linear, but may have a behavior which is smoother, more irregular, but that you can still characterize with a small number of parameters. So now in that case, in some circumstances, we are still able to apply the same type of ideas, okay? But the problem is more or less still open. The second thing is that if you have a trajectory which you really cannot model, okay, then your hope is that with this type of approach, you get a piecewise, for example, linear approximation of your complex trajectory, okay? So you would hope to still be able to estimate the field with a good accuracy, and then you estimate the trajectory. Now, not the exact trajectory, but maybe you do a piecewise linear approximation of the trajectory. I think this, this approximation question is also an interesting question to which I have no precise answer at this stage. So I think both questions are open. We have partial answer when we have a more complicated trajectory, but it is still parametric. We can do something in some cases, but not in all cases. So that's an interesting question. The other is, if I really cannot characterize the trajectory in any case, can I use these results to approximate it? And do I get good approximation, or what can I say about that? And that's, I think, an interesting research question. Thank you for asking this very good question, I think.
Yeah, thank you, sir, for your answer.
Sir, there is another question in the chat box that can this be applied for images or videos, and how?
Okay, good. So now depends on what you mean for this, of the things that I've mentioned. So there is some work on sampling a long trajectory to reconstruct images, okay? So imagine that there are some systems, right, where you, for example, get some, it's like this scanning system, okay? So you end up, let's say, with some information along a trajectory, maybe of an image, okay? But we don't have information outside that. Now, some of the ideas that we have here can be used, okay, in that context. There is the work by my colleague Pier, that area. Something I didn't contribute to, so that's why it's not in there, but there is a paper. I can send a reference if you are interested. So yes, so that idea can be used, for example, for images. Again, the results are not ultimate, are preliminary results. I think this is an open question, because images obviously are very complex signals. But there is some work in that direction which has potential. If the question was on whether the sampling based on timing can be used for, let's say, images or videos, because I showed only this 1D result, my answer is that at this stage we do not know, okay? We have done some preliminary work for videos. It's very preliminary, not published results yet. It is really an open question. And for people who are curious about this problem, I encourage them to look into this, because I think that there are a lot of potential new research that can be done in that area.
Thank you, sir. So, is there any other question from the attendees? I think there is no such question. Okay, I would like to thank our distinguished lecturer, Ms. Professor Dragotti, who honored this event with his valuable research ideas and this talk. I would also thank our coordinator, Professor Sudipta Mukhopadhyay sir, and our entire team of IEEE Signal Processing Student Branch and of IIT KGP. And last but not the least, our beloved attendees for making this event successful. Once again, I thank one and all present here. Thank you, sir.
Thank you very much. Thanks a lot for attending this talk and for inviting me. I really enjoyed that. Thank you. It was very nice interacting with you also yesterday.
Thank you, sir. Thank you very much. So can you just
Thank you
share
so much.
the reference paper which you
send an email maybe to Rahul with some references? Is that probably the easiest?
Sure, sir. Then I'll share it with the participants, all the participants. And so, Professor Professor wants to say something.
Yeah.
We would like to hear from you again.
Oh yes. Okay. Hope so. I hope to to interact more in the future. Okay. Thank you very much. Thanks.
Thank you very much.
Thank you, sir.
Thank you. Bye. Have a nice evening.